inch and a half. Is that what you said, Mark?
That works out well.
Yeah.
We got a special permit to be able to tie up to it today.
Very good.
All right. Okay, everybody. Welcome to the show.
Yeah, here we go.
Don't want anybody to feel they got rooked on the cost of admission. So, welcome and thanks for coming out here for this, and thanks for Maine DOT hosting the AASHTO TIG and the people that traveled from points afar. We're really excited about this because clearly this bridge kind of takes composite bridge technology to a whole new level beyond what it's been. And my partner Mike Zico and I used to joke about when we go to the bridge conventions that the composite guys were always relegated to a room down in the basement with about half dozen heretics that thought one day this might be a normal procedure. And with this bridge, I think we're one step closer. And I'd like to also acknowledge Maine DOT for having the courage to say we can do more than just a single span county bridge out in the middle of nowhere. You know, although this may be a bit of the middle of nowhere, it's also a beautiful nowhere. But regardless, it's a substantial bridge. Just in real simple terms, it's an 8-span bridge. The end spans are 60 feet. The typical interior spans are 70 feet. The girders are 33 inches deep, so that's a span to depth ratio of L over 25. All the beams are made continuous for live load over the supports, which to my knowledge is the first for a composite bridge. So like I said, the only joints are at the end of the abutments for a 540-foot long bridge. That being said, too, it's also designed for the HL93 plus 25%, so it's taken substantial load. We tested these extensive testing in the laboratory at the University of Maine AEWC Center. Took a prototype beam, ran 2 million cycles of fatigue on it, tested it for bending, tested it for shear. Literally could not break it in shear. We went to I think 300% of the code specified load. Ended up failing it in the bending mode with what would be an I always get these reversed, but let me think. It would be an operating rating of 2.6 and an inventory rating of 3.5. So substantial load carrying capacity. The rest of the structure you see too is designed by Eric Calderwood. Got steel casings, piles, concrete filled, the concrete cast in place pile caps, and then in between the beams actually stop about 8 inches short of each other, and there's a cast in place diaphragm that connects all the beams together over the piers. And then there's steel that comes out of the pile cap and crosses over. We call it a Freycinet hinge. So the interface between them, there's a shear interface between the deck and the pile cap, but it allows for some rotational capacity. When we tested these in the laboratory, we ran, I don't know, probably 52 channels of data that included, other than just deflections at quarter points and mid-span, we had strain gauges on the steel strands that are embedded in the bottom of the beam. We had strain gauges in the concrete arch, both top and bottom, so we could look at the forces in the arch as well as the gradient, if there's any bending gradient in the arch. We had gauges on the deck itself to measure the compression in the slab. And like I said, everything turned out to be very predictable, and got really good data from that. But the other thing that happens is in a laboratory, obviously in a very controlled environment. So, the load, we tried to simulate the HL93 load with a pair of axles, but that's, as you all well know, very different from what happens with real-life truck traffic and load distribution factors, etc. So one of the things we did with this bridge is, you see behind you, one of these interior girders, there's some duct tape on it. That wasn't to hold the beams together. That's actually protecting the lead wires that come off of the strain gauges. And we've got a very similar strain gauge arrangement in the beams as what we had in the laboratory, both on this beam as well as the adjacent beam on the next span. And the whole idea behind that too is that in the laboratory we were only testing a simply supported span, and in situ what we want to do also is be able to see what really happens with the live load continuity. I'm trying to think what else to say about it. I don't know how many of you have seen the HCB yet. I don't want to go into without waving my hands. It's going to be easier later to look at pictures if you're not familiar with it to see what it really looks like. The other thing that we want to do with the structural health monitoring long term, and I think this plays into questions you might have with the AASHTO TIG, is one of the questions that always comes up is UV protection. So the gray color you see in this is a pigment that's added to the resins, which gives us UV protection. The fascia girders, the exterior face and the bottom of all the fascia girders also get a post-applied gel coat, which gives us additional UV protection. One of the things we're doing for environmental testing is for each one of these beams that was fabricated, we shot witness panels, which is just a small sample of the laminate that's the exact same glass resin lots that were used to manufacture the beam. And the idea is to take those and put some of them, put a handful of specimens out here on the bridge, where they'll be exposed to the same environmental conditions that the bridge will see, and then to keep a handful of them in a controlled environment in a closet somewhere in Orono, and then periodically take out one of each and test it and see what kind of changes we see in the laminate properties as a result of UV, moisture absorption, salt water environment, thermal loads, and there's already some things that the university's done with thermal cycling, with just some tests, coupon specimens where we've run 120-degree thermal cycling and tested the strands to verify that the strand actually fails. We're actually breaking the strand in tension before we get any pull out or slip between the laminate and steel. So I could probably talk all day. That's probably more than I want to hear right now, but I could answer a few more questions, or you can talk amongst yourselves.
These things are obviously very light. You said that, was there any issues with stability? You don't have a...
No, I don't think...
No, they weren't. And they're so wide on the bottom because they're 2 foot wide. There was no issue.
Pretty stable shape.
The other thing is they put them down close and they just take like a bar and just move them wherever they need it.
These, you've got the little flanges so that they would interact with it.
Right.
Yeah, but there was no obvious wobble on them or anything. Even whenever you were moving construction traffic on top.
No, in fact,
Pretty
Stacy,
stable.
these beams, these 70 footers you see empty, these only weigh 5,000 pounds.
That's what I remember.
And in fact, there was no temporary diaphragms or cross bracing when they were set in place. Wyman Simpson were able to set 8 beams, actually 16 beams in a day, I believe it was.
Maybe 12, but yeah,
A lot of beams in a day. And then they were actually able to fill the concrete arches, actually pump the concrete into the arches.
You pumped it?
Yeah.
No,
Well,
free fall.
free fall with a trebuchet, but they were able to do that again without any lateral bracing.
How about load training? Not into that.
We're actually looking at that right now for Stacy's bridges in MoDOT, because MoDOT's got about 42 trucks that you guys like to.
Yeah, we have all our routine permit trucks. We just pre-rate everything up front. We don't have to.
I'm a little concerned you got 42 routine trucks.
When you have wind farms and et cetera, so on and so forth.
But
And we're also we're the crossroads of America in Missouri. I mean, you cross the Missouri River in St. Louis. If you look at the traffic patterns, we have a lot of.
plus they don't believe anything we tell them. We got to show them.
That's right. and incidentally, one of these bridges that he's building for us is on a major rural expressway, so
Yeah.
it's gonna receive a lot of traffic.
Yeah, but what we are looking at that, Lou, both for bending and shear, and looking at both the inventory and operating ratings. And it's I'm not as familiar with Vertus or Pontus. I mean, the idea is to put it in the same format. And the question is at some point, can we also get that into Pontus so that the DOTs have that available to them?
Well, we can talk about that later. We'll accept the hand rating like we talked about it.
Yeah.
No, because when they're empty, you can actually pick them up in the middle, or you can pick them up at either end. So if you had a 90-foot long beam, so you probably have 20-foot overhead. So if they were shipped from basically because that's the way the trailer is down.
For Stacy's bridge, we don't have the overhang flanges because we're going to use precast deck panels in between the beams. So in that case, we can actually ship 8 beams on one truck.
Was any consideration given to the launch of these being betterment possibilities?
I don't think so. Not in the normal convention that you would launch like a steel or concrete bridge, because you'd have to either have temporary supports, or you'd have to have some sort of temporary continuity that allow you to get the negative moment capacity over the piers.
Did you mention there's a concrete deck on top?
I don't know if I did, but there is. Again, when you get into the whole embodiment of it, I mean,
Right.
you've got the concrete arch inside, and then there's got a 7-inch normally reinforced concrete deck on top. Again, we used to use the main DOT standard for a 7-inch deck. So it's got number 5 bars at 6 inches both ways transverse, and then number 7 bars at I think
Over the
5 or
pier.
6 inches over the piers. And
For negative moment continuity.
Yeah.
Why not use fiberglass rebars or carbon fiber rebars instead of just to make the whole bridge?
It depends. I mean, we're looking at that with this pier that we're doing up in Machias right now, where certainly with the transverse bars, I don't think there's going to be any issue with using fiberglass bars or
Right.
carbon. But even fiberglass should be fine. Longitudinally, it becomes a little more difficult when you start looking at the negative moment capacity of the piers because it's still a strain compatibility issue. You still need
Right.
the high modulus of steel. Not that you couldn't do it with glass, but you'd end up with a lot of reinforcing, probably more than makes sense.
Why don't these transoms need to be composite as well? They're just raw concrete, right?
Yeah.
They could.
Yeah, in fact, again,
Could be.
the pier that we're
Maybe
doing up in Machias,
expensive.
Maine will actually have an HCV pile cap as well. We've already fabricated those.
So is this I hesitate to say at a weak point, and I mean, could this deteriorate faster than everything else here?
It's possible. I mean, it's
It's protected to some degree because you got everything above it. It's protected, so yes, it could, but it's probably not very possible.
it's always tricky to identify weak links with the medium.
Now, one thing
Let's just say these should ideally outperform this. That's an idea.
You told me earlier you invented this 15 years ago, right?
Yes.
What gave you the idea to do this, to go this far?
I was just crazy, I guess. No, I've been a practicing bridge engineer now for 25 years, and I've had the good fortune to be exposed to a lot of different types of bridge technology and materials, whether it's post-tension concrete, high-performance steels, and I had some exposure with fiberglass when I was in grad school as well. So it was about 15 years ago I ran into this manufacturing process for composites, which is vacuum-assisted resin transfer mold, VARDM for short. And again, it's just one of these epiphanies where it's like, wow, why couldn't I put a concrete and steel arch inside of a fiberglass box? And that really started the journey. So I filed some patents on it, started doing some calculations, got some research grants, and went about the process of validating it. And probably the hardest part is it literally took us about 6 years just trying to figure out how the process to build and manufacture a composite of this complexity and this size. Not that there's not large composites. I mean, wind blades now are huge, but 15 years ago, I mean, composite parts were like car bumpers and small pieces, hard hats, and certainly boating technology was there. Aerospace was very sophisticated, but to get to a large-scale, heavy civil application like this, it was very unusual. And then combine that with the fact that we were putting in these steel and concrete components, as opposed to just a pure composite laminate. So the hardest part, I think, was really figuring out the manufacturing process, and then getting it to a point where it was a cost-effective and reproducible system. And again, this bridge is a classic example of that because we've gone from composite structures that are typically anywhere from 5x to 10x the cost of a conventional structure to these beams here, which were on par with concrete. So the people who say the Maine really did not pay a premium to have the composite technology on this bridge.
What is exactly the manufacturing process that you've got to do this?
Well, that's double top secret, right? I mean the vacuum, the VARDM process essentially amounts to charging a mold with. It's no different than building a big boat hull, where you put in your fiberglass, your steel, your foam, you close everything up in this closed mold. You pull vacuum on it, and the vacuum evacuates all the air, which gets you a lot of compression on your composite part, which you really want. And then once you're holding vacuum, then you basically pull resin into the mold. It wets out all the parts, cures, and then you pop out the finished piece. And the vacuum really is the key to it. And not only does it pull the resin through the mold, but the quality of the composite is much higher because the compaction gets this very high fiber volume fraction. What that means is that 60 to 80% of the laminate is actually glass fiber, which is where all the strength and stiffness comes from. So it's just a very efficient process.
Is there any limit to the size that you can make?
Yeah, there is. I mean, the process itself is scalable, and yeah, there's no reason to believe that you couldn't build a 200 or 300 foot span if you really wanted to try it. We really don't have an interest in doing that, partly because if you look at the bridge statistics, of the 600,000 bridges in the National Bridge Inventory, something like 95%, at least 95% are less than a 100-foot span. So we've kind of targeted the sweet spot is up to about 120 feet. Could we do something longer than that? Probably. Do we want to? I don't think so.
So the max that you're looking at right now is 120?
Yeah.
That can be done. What's the depth of the total depth of this superstructure right there?
The total depth of this one is
7-inch? There's a 7-inch deck.
7-inch deck. So the total depth of this is 40 inches
40 inches.
on a 70-foot span.
That's